Hi, my name is Richmond Baylon, and today I will be covering some concepts from Chapter 22, Electricity and Magnetism. Before we jump in, let's talk about electrostatic. First of all, I have to define what we're actually looking at. Electrostatic is the study of electric charges and how they interact with each other. There are two charges, electrons and protons. Electrons are a lot lighter in weight, whereas protons are a lot heavier. We know that atoms are made up of electron, neutrons, and protons. We can look here in the Bohr's model. So the Bohr's model actually shows the model of an atom and their general arrangement, where the protons are in the center and the electrons are outer shell. So by nature, we know that charges can either repel or attract each other. Like charges repel each other, whereas opposite charges attract. Before we move on, I'll show you a demo I did last night, and hopefully, that works.
Alright, so you'll notice two things. One, I'm still in my pajamas, and two, that this test is actually really easy to replicate. What you just need is a PVC pipe, firm material, and some empty can, like metal tin, you get that anywhere. Okay, but who's a person who actually has a material like actual fur and a PVC pipe just lying around? So instead of that, we have some substitutions. So the first thing we need is a can, and that's pretty accessible. If you're an American, you probably drink a lot of those with sodas. Instead of a fur material, we have a microfiber cloth, and I couldn't find anything that is rod-like that like most people would find. So instead, I realized the closest thing I have to that is this really expensive lightsaber. You can just get this anywhere, it's totally replicable, but yeah, so we're gonna do the experiment like this. So the idea behind this experiment is that this can here is actually a conductor with free moving charges. Without doing anything to it, other than holding it up, it's a neutral charge. So that means that if I leave it here and I grab my rod, which is, of course, the lightsaber, it won't do any attraction or repulsion because I haven't done anything to the lightsaber yet. Yeah, see, that's kind of lame. Alright, so what you're going to want to do is you're going to grab your microfiber cloth here, and you're going to rub it against the blade, just like in the movies. What this does is effectively remove the electrons from the areas I'm rubbing, leaving only positive charge from the protons in this rod, or saber, I guess. Okay. Woo! Isn't that sick? I'm using a lightsaber to attract this freaking can. I'm trying to not touch it though. Alright, let's go the other way. Woo! That's sick, is it? Dude, I'm using force. I'm actually using force. I'm a Jedi.
So some things I mentioned from the demo. A conductor is actually an object or material that allows charges to move freely within itself. The force I mentioned from last night is actually electricity, and what I showed in the demo is that electricity is actually a long-range force, meaning that I didn't actually have to make contact with the can with a lightsaber to make it to move. When I was talking about how I was charging the lightsaber, I was actually talking about how I removed the electrons from the outer shell. So what I basically did is I grabbed the cloth and I took away all the electrons from the outer shell of my PVC bar. I tried to do this in front of the camera in the demo by actually grabbing the cloth and rubbing the saber. By doing this, I actually removed the electrons from the saber's surface, leaving only behind the protons there. This allows for an induced polarization. So first, let's define polarization. Polarization is a separation of charges into distinct regions like positive and negative. You can think about it as like a magnet, where one side is very positive and the other side is very negative. And then if you try to take two magnets and have the same charges try to interact with each other, they'll try to repel each other and they won't actually attract. Whereas if you have two different ends, they'll actually attract and then stick together. Induced polarization is what I did in the demo, where the separation of charges actually occurred in the conductor, which was the can, and then the presence that I used to separate it polarize it was the lightsaber when I charged it. Another thing to note is that induced polarization is not permanent. So as I leave the lightsaber and the can in their places from last night, they actually regain their charges. from other sources, much like probably the table or the air, or maybe when I touched it. So they're back in neutral charge. So now we can establish that electricity is a long-range force, and we're utilizing induced polarization for it to move. Since a can's a conductor and the charges are free to move using a charge presence of a rod, so positively charged rod here actually attracts the can's electrons for it to move, hence a long-range force. This is actually analogous to gravity, since gravity also is a long-range force. If you just grab a pencil, right? It doesn't need any contact for it to go down. Gravity is also a long-range force that doesn't need contact with anything for it to bring an object to accelerate downwards. I'm not gonna drop this. Is too expensive. I'm not gonna drop this one. I'm sorry. I don't know why I picked this up. Actually, I could do this. I don't want to think. I've dropped this a lot. Now, if only there was a formulaic way to actually describe the interactions between two charges. So Coulomb's law is a physical law that describes the interaction between two charges.
So Coulomb's law is actually analogous to Newton's law of gravity, and we can observe it like this. Force equals Coulomb's constant multiplied by the charge of 1 and the charge of 2. So these are two different charged particles here, whatever you're observing, and then the distance squared. And then there's going to be the r hat, which is just the unit vector that's telling you direction. We can observe from here that as distance increases, the force actually decreases. So when two of the charges are actually close to each other, so the distance is smaller, we can actually tell that the force is very large compared to when the two charges are far apart. Therefore, the distance is larger. Therefore, the force is smaller. R hat is just a unit vector. Since force is a vector, it will also tell us a direction. And then Coulomb's constant is actually 9 times 10 to the power of 9. The units are newtons per meter squared divided by Coulomb squared. We can define these two units to be coulombs. And then R hat is just a unit vector. It tells us direction, which is very useful. And then R squared over here, this is the distance. And this is going to be in SI units, so this is going to be in meters. And we can tell with Coulomb's constant is going to cancel out a lot of the units, and it's going to leave us only with newtons, which is very appropriate since this is a force unit. Okay, so now we'll actually jump into an example question that utilizes Coulomb's law and trying to solve for a particle's net force value.
So now we're ready to actually jump into an example question. So the question here is, what is the net electric force of Q1? And on the side here, I gave us some data. I'm going to give us another one when it becomes relevant. So we know that Q1 has a charge of -1 times 10 to the negative 6 coulombs. Originally, this question was in microcoulombs, but I decided to actually just clean this up for us so that we can actually have the correct SI units to save some time. So everything's in the correct SI units. Right now, we just need to solve it. So we just see here in space, there's nothing to really guide us on how to solve this question. So the first step is actually to establish a coordinate system. So I'm going to make Q1 the origin of our coordinate system. Why, you might ask? It's actually because what we're solving for. So it's a lot easier to just work with this. Q1 actually can line up with Q2 if we establish an x-axis this direction. We're going to establish this as x, and we're going to say that this is the positive. We're going to say that this is the positive direction. You don't really have to do that, but it's just something that I like to keep track of. And then over here, we're going to do... So over here now we establish the y-axis, and of course you don't have to do the plus sign there. I just like establishing that. Okay, so that's all nice and all, but how are we going to find the net electric force? So this is the next data piece that is going to have to be given to you, and I have to do it right now. So if I were to connect Q3 to Q1, we know that the distance is actually 13.02 meters, right? So distance isn't an issue. Since it takes on both x and y coordinates, we're going to have to find the angle in between when solving for this. We're just going to call this theta. So I'm going to have to give you the angle for this one in order to solve it. We're going to call theta 30 degrees. Okay, so now we're actually ready with all the information to solve this So step 1 was to make a coordinate system. Step 2 is to actually establish where the forces are going. So we didn't write this down, but we can actually write down what each particle charges are. So we see that Q1 is a negative 1 times 10 to negative 6 coulombs, basically a negative sign. So we know that Q1 is actually an electron. Q2, on the other hand, is actually a positive value, so we know that this is a proton. And then we switch signs again. Now it's a negative value for Q3, and now we know that this is an electron here. So now we have this all labeled. We know now how to draw the forces that's going to be imposed on Q1. So now that we actually labeled them as electrons and protons on the grid, we can actually check for the direction of the forces. So the force that's going to be imposed on Q1 from Q3 is going to be that of a repulsive force. And we know this because they're the same charge. So I'm going to draw this with red. We're going to point it this way. And we're going to call this F of 3 on 1 because it's the force of 3 that's opposed on 1. Next, we know that opposite charges actually attract, and we see that Q1 and Q2 are opposite charges. So the next force is going to actually point from Q1 to Q2. We're going to label this force of F2 onto 1. Okay, so great. So now we know the direction of the forces. We can kind of get an idea of where the net force is going to go. So we're going to actually start with force of 2 on 1 because it's a lot easier since they're actually lined up. So there's Coulomb's law here. Coulomb's law. So force of 2 on 1 equals, so Coulomb's constant is K equals 9 times 10 to the 9th power newtons per meter square over Coulomb square. Okay, so now we're going to input the data. We're going to put Coulomb's constant. All right, don't forget to include units because it would cost a lot of money if you destroyed a whole rocket. Okay, so now we're going to input the value of Q1 and then Q2. And now we're going to divide this by their distance, the distance between Q1 and Q2. And then this is going to be squared. Now for the directions, we know that Q1 and Q2 are lined up in the x-axis, and then there's nothing, they haven't moved anywhere in the y-axis. Now furthermore, we know that Q2 on 1 is actually going the positive x-axis, or positive x direction, that is. And because of this, we can keep the x-axis value as a positive. We're going to keep the first component x as a positive value. So if we calculate this, it's going to be 10.8 I to show that it's an x, and then plus 0j, since there's nothing in the y-axis between these interactions.
Okay, so now we're going to do a force 3 onto 1. And if we scroll back up and observe here, we can tell that now it's a little bit different from our previous problem. The previous one, we didn't have to take into account any y-axis since Q1 and Q2 lined up perfectly on the positive x-axis, or I mean on the x-axis in general, at least how we configured it. However, now we have Q3 that is taking into account both x and y axis. So this new direction difference we're going to have to take into account when we do our problem solving using Coulomb's law. But for now, the great part is that we just do business as usual until we take direction into account. Okay, so business as usual, we're going to do force of 3 on 1. Okay, so now I'm just inputting Q1's value, which is that. Now I'm inputting Q3's value of negative 2 times 10 to the negative 6 coulombs. Okay, so now we divide it with the distance between these two particles, which is 0.02 meters. Okay, so from here, we should get a value of 45. Now, we're not really done here because we still need to take into account the direction. So since we set up our theta to be along the from Q3 to Q1 and then up against the y-axis, we're going to have to start with the x component with sine of theta, and then our y component with cosine of theta. And we can see that theta's value is 30 degrees. So we take 45, we do sine of 30 degrees. So this is the x component. And then we're going to do 45 cosine of 30 degrees. Now, before we actually solve this, we still need to take into account where the vector is pointing. We can see that the vector of force of 3 onto 1 is pointing to the bottom right. So that means the x component is going to keep a positive sign. However, now the y component is a negative sign. So instead of a plus here, we should actually have a negative symbol, or, well, minus. And then after we compute this, we should get a value of 22.5 I, so positive x direction, and a negative 39.0 j. So this is how we find the F total, or the net force that's imposed on 1. From here, you should get a force total of 33.3 I, and then negative 39.0 j. Thank you so much for watching. My name is Richmond Baylon, and I hope this helped you maybe learn, maybe understand a little bit more about electricity as a long-range force, and how induced polarization is an example of long-range force. I hope I helped out a little bit in trying to explain how to solve for charge, at least net charge in this example, of a particle that's interacting with another charged particle.